Okay, so let me continue with these things just to give a recap. Um, this the first step in this method to model check LTL is to convert the property that you want in our formula that you want to verify into a transition system by just using the structure of the formula to make its determine its states and the laws of the temporal operator as per the LTL semantics to define the transitions. Such that the every trace that satisfies a formula is included in that transition system. Okay, so we saw the examples for X and the until operator. Okay, and so I want to show a couple of more examples today where the operators, formulas involving for LTL formulas that use nested operators. Okay, so we will get back to this details of the definition if you have any questions during while I illustrate those examples. Okay, did any of you give it a try to a nested operator to construct a tableau for it? No? Okay. Let me do it. So is this, I hope this is visible. So here is a formula. The formula is A until phi1, where phi1 itself is xb. Okay. So just X is nested under the thing. So how do you start, in constructing the tableau, you will have to first determine the states. So how were the states determined? Do you remember?
Should be elementary.
Yeah, so first you get the closure of the formula, which is all the sub-formulas, okay, of the original formula, including itself and their negation. And every elementary subset of a closure, the closure set is a state in the tableau transition system. Okay, and that's what here say. So in this case, there is A, not A. So A, phi, and phi1. Okay, and their negated version. It should be 6, no? 3 and yeah. So A and A 3. A, there's only A, phi and A, phi and phi1, and the negated version. Yeah, so here, how come I have 4? Phi itself is 1. There is also B, I'm sorry. There is A and B, okay? So with the negated version, so I have 4 bits, okay? So it's 0 and 1 for each of them. So there are actually 16 possible states, okay? And so 16 possible states. So since the elementary set has to be maximal, so either you have to include either the for each subformula, it's in its positive form or its negative form. Out of those, I've eliminated already those that are, I've only kept those that are elementary, in the sense those that violate the prepositional consistency and local consistency. I have eliminated, and things that are not maximal. So these are the remaining states. So in the initial states are the ones that contain the original formula in its positive form. So that's why. So the one that, so here the order, I haven't shown the order of the bits here. I assume it's A, B, phi 1, and phi. Okay, that I've not shown, but assume that it is A, B, phi 1, and phi. So that's why the one which has 1 as its least significant bit are the initial states. So then now you have to define transitions, okay? And as I said, the transitions are defined so as to preserve the expansion, the rules of phi 1, the until operator, and the X operator as they may appear. So in this case, since so you both have subformulas in the states that are rooted at U as well as X, okay? And so you will have to define the transitions so that both these laws are preserved. So as so that's how you define, and then you will have fairness conditions for every subformula that is rooted at U. So in this case, there's only one such subformula. Okay. So let me show some transitions. Okay. So I hope you can read it, right? So this state S0011 contains not A, not B, and phi 1 and phi. Okay. So since it has phi 1, so there must be, as per the rule of X, it should have a transition from this state to a state, the next state, a successor state in which B is 1, correct? Now here. So why is this transition that I've shown here in dotted arrow is not permissible? Can anyone tell me? Or the ones that I have crossed out are not permissible. Why can I not have a transition from this state 0011 to 000?
Because XB is not negated, so any next state should have B, right? B is
Correct.
not negative.
Correct. So it doesn't preserve the X rule. Okay. So the idea is to define the transition such that every path, infinite path, fair infinite path, originating from that state makes every formula, elementary formula contained in that state to be true. Okay. So, and that is done by defining the transition as per the semantics of U and X, the recursive semantics, those laws that I showed you exactly define that recursively. So similarly, that's why all these crossed out arrows are not there. So as per phi, a rule of U, is a transition permissible from S0011 to all zeros? I know this is not permissible because it's violating X, okay? The rule of X. I'm just asking you the question. Since both have to be preserved, you know, so that's the thing. But I'm asking the question, if...
No, I mean either phi 1 should be true next, or both A and AU phi 1 should be true next, right?
You see? Okay, so let me... so in this case, phi is... the until operator only applies to phi, correct? Okay? So phi is true here by virtue of the fact phi 1 is true. Once it becomes true, it doesn't matter. Okay, so in this thing, you know, phi 1 is
Oh, right, yeah.
completely true. So if you did not have XB, you could have had, because once it becomes true, it doesn't matter, correct? As per the U semantics, okay? So you can have anything, okay? So that's why if it were not for the X, you would have this this transition, okay? And yeah, so whereas the self, okay, I think I made a mistake here. So I've shown the self loop here. It's you know, no one caught it. Okay, the self loop should not be there either. Correct? For the same reason. So XB, B is false. So in the next state, since XB is true, it can only have transitions to those states in which B is true. So this should be crossed out also, okay? And that's how that you define. So there is a mistake is what I'm saying. So this is how you fill out all the transitions. I've shown only some of the transitions as an exercise. I will leave it as an exercise for you to complete this tableau, okay? Any questions? Okay, any questions so far regarding how you complete the transitions? Okay, now, yeah, this self transition is fine, okay? Because it preserves the XB, because B is true in that state. And since phi 1 is true, you know, so already the, you know, phi is already true. So it can, you know, there's no harm in it continuing to be, you know, to be true. So the transition from 0, 1, 1 20100 is just fine, okay? Because this is XP. So once phi is true here, after that, you know, you can either continue to be here or you can actually go to any state. As a matter of fact, yeah. So that's why this thing is the case. Now, what is of interest is this state. Okay, this is the state like S1001, which is what necessitates for you to have this fairness constraint. Okay, so here, phi 1 is in its positive form, okay, but it's not yet true, okay. So it is potentially true, whereas here in the 00011 state, phi 1 was, or you know, definitely true. Whereas here it is meant to be true, but it is not yet true. So it has to actually eventually visit a state, you know, in which phi 1 becomes true. Okay, and until that time, it has to preserve, maintain A to be, keep A true. Okay. So, and since that can be indefinitely long, so this one, this self loop here is not a, you know, the path which continuously takes the self loop is not a fair path. Okay, so while I have not completed the thing, so you would say, oh no, yeah, so this transition from 1001 to 1011 fulfills that obligation, because there phi 1 becomes you know, true, and after that you can you know, go and then keep looping in this state, or you can keep self looping in this state. So that's why, so you define the fairness condition in such a way that you exclude these things, states like 1001, from your fairness condition. Okay, so as a matter of fact, that's why you define the fairness condition. There is one set of fairness condition for every every formula in the closure which has a until operator at its root. There's one corresponding to that, and it is defined in this way that it includes, you know, you have to only make those, you have to visit those states in which phi 2, the second component of that until operator, becomes true. Visit these states in which this condition is true infinitely often. And you can end up, you know, then one in which you know, phi 1 until phi 2 formula is completely false, because the transition is defined in such a way that there is a transition. There's always a transition from you know, such state into phi 2, and therefore it is by making phi 2 and you know, these not of phi, including them as part of the constraint, you will fulfill that thing. And that's why what is included in the fairness constraint corresponding to the only sub-formula in the closure that has a root at its root, the until operator, are those ones in which it's the phi 2 component, which is phi 1 here, that part, okay, the second argument to the until operator is true, or this entire, those states in which contain not of phi, because once you reach the state in which phi 1 becomes true, after that you can transit and keep visiting the not phi states infinitely often. To make provision for that, you include those things as well. Okay, so and that's how that you that you do. Yeah. Yes. Any questions?
So I couldn't understand why there was this. So the phi one until, so in the previous definition, the A until B not belong to S condition in the fairness condition. Why was that there?
So why should you have this?
Yeah.
Not phi. Precisely for the reason that once, see, the transition constraint, the expansion law ensures that there is a transition from this state in which, here phi is potentially true, not it has not become true yet. Okay. So once you reach this, after that, the infinite path may have the suffix could be something, the suffix after that can be where not phi never becomes true again. That's okay. See, it has to
Okay,
all paths, okay? And the way this tableau is constructed is all possible ways in which every subformula, okay, can be true has to be included, okay, in this thing. Since paths that satisfy the until formula that begins with until can, after it is satisfied, can have not phi for arbitrarily long after that. So that's why you include this as well. Okay. So for example, when you go from here to here, so here phi is not yet true. Okay. As long as you're here in B3, so phi can potentially eventually become true. It is still preserving the constraint. So whenever you have a liveness kind of a requirement, then for it to be true, you will have to first visit a B state, which is true for B1. After that, you're permitted to loop around in B4, okay? That is fine, okay, to account for that. That is also, or you can have, go back and forth between B1 and B4, or you can continuously loop in B1. They are all infinite paths that satisfy phi. In order to account all of those things, that's why you also include B4 in your fairness constraint. Okay? B4 and B5 are the two states in which contain not phi. Okay? So as far as paths that satisfy phi is concerned, you can end up visiting on some paths where that is true, infinitely true, often true, okay? That's why you have both these things.
Yeah.
Yeah, and what is important to observe is, so here you include both, but you define the transition, so you might end up thinking, well, what if there is no transition from here to there and then you never end up transiting? So, but this transition, okay, this expansion law for this will ensure that, there is a transition from B3 to a state where the second argument to the until operator becomes true, which in this case is B, okay? And then you get to B4, only you see there is no transition from B3 to B4 or B5, if you notice, okay? There's no direct transition from that. That's important to note, yeah? So by including this not phi, you might be worried. Okay, maybe that's why you are asking the question. So, can I not just end up going to B4 or B5 directly from B3 and then staying there forever? Okay, which will violate the semantics of U, and that's why there's no direct transition from B3 to B4 or B5, because that is not allowed by the expansion law. Okay. So here you can either transit to something where phi2 becomes true, or phi1 should be true now, and you can only transit to something in which, phi1 until phi2 from then on is recursively holds. Okay. So that's the important thing to notice, and that's why, by following these expansion laws, okay, so you exactly and defining the transitions, that is what ensures you by construction that every path, infinite path originating from that, every fair paths, okay, the fairness condition will have to eliminate these infinitely staying in these kinds of things in states like B3. Yeah, so as you can see, this whole thing can be done in a very deterministic, finite elimination. So you will have to just, you can see there are only finitely many sub-formulas, and you see that this, you'll have to do this, I've kind of enumerated and then eliminated, but you can use cleverness in eliminating, checking for the local consistency and so on. And, so you have to look at even the fairness constraint, and everything can be automatically generated. So pretty much this tableau can be automatically generated by just looking at the structure of the formula. Here we are not. This is being constructed. One important thing that you should observe is this is being constructed independent of any particular model for which you want to check if this particular formula holds good. Okay, that's the next step, where we will use such a tableau to check if a particular Kripke model, a particular transition system satisfies phi or not. Yeah. Okay, so any questions here? If not, I'll move on. So here is an example where an until operator, is embedded inside another one. Okay, it's nested inside another one. So I have phi A until B until C. Yeah. And A until B, the first argument to the until operator, top until operator itself is an until subformula. So you will have 32, 2 to the 5 states, okay, potential states, subformula of the thing, but most of them can get eliminated by the consistency and local consistency checks. What remains is still quite large, okay, these are the ones that are, that are there. And, you can, I'm not going to go through, the detail, but I'll just observe one thing. I'll ask you just to see if you understand. So once again here, it's A, B, C, 515. That's the order in which I've defined the bits. Okay? And as you can see, this is a state in which both phi and phi 1. Phi 1 is, expected to be true. Okay? This is A, B. So since B is true, obviously phi 1 has to be true. Phi can be true here or may not be true, okay? Here, phi, so both are possible. That's why S0, 1, 0, 0, 1, 0, 1, 0 is also, 0, 1, maybe 0, 1. I thought 0, 1. Actually, anyway, I thought 0, 1, 0, 1, 0 at least is not possible. Why? Because 0, 1, 0. Okay, so as you notice, at least I have not included 0, 1, 0, 1, 0. Okay. Why do you think 0, 1, 0, 1, 0 is not possible? That's a good question. Hmm. 0, 1, 0, 1, 0. I think I might have made a mistake there. 0, 1, 0, 1. Yeah, I missed out on that. So, yeah. I mean, let me ask you a question. Is 0, 1, 0, 1, 0 possible? That is, what I'm asking is it elementary? Is this combination 0, 1, 0, 1, 0? That is, A, not A, B, not C, phi 1, not phi. Is it possible? I think it is possible. Is it? So I'm asking you the question. Is 0, 1, 0, 1, 0? Yeah, I think it is certainly possible because phi 1, no. Oh, okay. Yeah, so it is quite certainly possible. So let me write it out so you will see. So I want an answer to make sure that you guys understand. So what I'm asking you is this one. Is it elementary? Anyone? Remember, phi is okay. So look at this. See, phi 1 is supposed to be true here. Yeah. So B can be, so phi 1 is true since B is true, so that is fine. And phi may or may not be true here because it is still preserving because C is not true yet. Okay. So as long as, yeah, so you can, since C is not true, even though it might be true, it is preserving phi 1 is true, C may never eventually become true, in which case not phi, phi may not be true. So that is a possible state, okay, that I have not, by mistake, not included. But nonetheless, the point that I want to, is that clear? Okay, so I don't know, you guys, no one's answered it, but so I want to make sure that you understand. Okay, so in this state, 0, 0, 1, 0, 1, 0, 0, 1, 0, 1, both 1 and 0 are possible. Okay, and that had to be included. So let me ask a question. So this is something that you need to understand. So if you don't understand, either you will have to ask question or you will have to think. Why is this transition, the dotted transition from 0, 1, 0, 1, 1 to all zeros I have crossed out? Can anyone answer?
Then B until C will not be true.
B, that is, yeah, P1 until C will not be true.
Yeah,
Because you want that to be true here, and if you go there, it will not be, that thing will be violated, the expansion will be violated. Good. Okay, so that is good. So, yeah, so that's how you fill all these, all these things, and you can, as per the expansion laws, and, so both the expansion law for the until, there are two until subformulas here, phi and phi 1. Both of them have to be true conjunctively, okay? So it's not okay if one is true and the other one is false. And since there are two such subformulas, you'll have two separate, fairness condition, one for phi 1 and one for phi, exactly defined the way is defined. That includes the negation, those states that include the negation of the formula, and the ones in which the second component, the second argument to that until operator is true. And remember how fairness constraints have to be done. So the fair paths are defined as one in which the one of the states in if phi and one of the states in fi1. Both of them will have to hold good. Both conditions have to hold good infinitely often, in the sense that in a strongly connected component that your prefix will eventually reach one of these states that is included in phi and one of the states included in fi1. Both have to be present there, and that's why it'll ensure that the fact both constraints have to hold good will ensure that both these formulas, if they exist in its positive form in a particular state, will end up preserving the liveness constraint through the fair parts. So, so one thing I want to emphasize, so it's only the fair parts, okay, this property that I just now mentioned, that every formula included in the in a particular state, every that is true only of all the fair parts originating from that state, okay? And until operator is the only one that has a liveness requirement and a fairness, because X does not does not have any no need for that to have a fairness constraint. That's why you have fairness conditions defined for every until sub-formula in the thing, okay? Yeah, so that's how you define. So as you notice, there is one mistake here. There is a missing state here that you will have to include. So as an exercise, I very much encourage you to complete this tableau. So two main correctness theorems. Okay, I will state the theorems now and illustrate the whole thing. And if I have time, I will maybe discuss a little bit more in the next class. There's interest. So here is the main theorem that actually formalizes this notion of construction of the tableau. So let T phi be the tableau for the LTL formula phi. Then for every Kripke structure n, every arbitrary Kripke structure n, and every path pi prime in that n, if pi prime in that pi prime in that f, it satisfies that formula, then there is a fair path pi in the tableau starting in a state S such that phi belongs to S. And if you just keep the labels on the paths, okay? So M can have its own state and it can have its path, okay? So for every path in M, for any Kripke structure that shares the labels, okay, the concerned labels, if it satisfies phi, then you will find a fair path in the tableau such that you will find a state and a fair path from that state that satisfies phi, because as I noted, T phi by its construction includes all the possible ways in which base beans scenarios, infinite paths, in which phi can ever be satisfied by any Kripke structure. Okay, so that is the way, and that's why you could use this tableau, which is constructed independently of any particular transition system, to check the transition system to see what this means. So let me use this example. Okay, let me go to make this bigger. So remember, this is the microwave example, okay? I'm considering the property not H until C. H here stands for heat being true, and C stands for close. H stands for heat, C stands for close. If you notice, not H until C is true in every state of this microwave transition system. It is true in 1 because there is a path from there that leads to something which eventually close becomes true, and until that time heat remains false. In all these, in states 3, 4, 6, and 7, it is vacuously true, as well as in 5. So in 2, in one step, it becomes true. So it is true in all states. Okay, so there are different ways in which this property, not H until C, is true for these things. In 3, 4, 5, in 3, 4, 5, 6, and 7, it is immediately true by virtue of C being true. So that means that corresponds to this behavior. Okay, so you see, phi is now not H until C. So this is the tableau. Okay, and the way I got this tableau is exactly, this is an until operator. This is just you instantiate this one with not H for A and C for B in this in this thing. So that's how you got this. So you will see that for 3, 4, 5, 6, and 7, you have 5 being immediately true, and therefore that corresponds to the state marked here as T2, okay, from which contains phi, that is not H until C, and it is immediately true there. And after that, and as you can see, it kind of either remains there like it is here, or you can end up going circulating into something in which it may temporarily become false but eventually become true. So anyway, so what you will see is that's what this is being stated. So for any crypt key structure, as long as the labels are consistent, that is what it is. So if phi is true, so you extract. Okay, so that's what. So what I'm doing here is when I do label of pi prime equals label of pi, so you will see that if you just get the labels, the trace, containing only the labels, then for every path here in any model, in any crypt key model that satisfies this property, you will actually find a state here in the tableau which contains that formula and then mimics that particular satisfying path in the tableau. And that's because by construction, the tableau.
Sir, I'm confused. What is label?
A label is these predicates. Okay, remember that how the crypt key structure is defined. Okay, a crypt key structure has states, initial states, transitions, and a labeling and a label set AB. Here, the label includes
only atomic prepositions, right?
The atomic prepositions. Correct.
Okay.
Yeah. Okay. Since we were talking, because the execution path is a sequence of states, right? So, I mean, the states on an execution path here, you cannot compare them here because the states might be different here, okay? The paths, I mean, the states that appear on the paths. That's why the only way you can compare two different crypt key models in terms of whether they satisfy, both satisfy a particular property or not, you will have to take the labeled version of that. And that's what I'm doing. So, and that's what this thing, for each state here, I'm including the atomic propositions. And that's what I'm doing, okay? Yeah, and if you look at state 1 in the microwave of an example, that there it is not immediately true there, but there is a path from here to here, okay, 1 to 3, where it becomes true, okay, right? And after that, you can keep going back and forth. That is mimicked by the path starting from T1 here in the tableau, in which you cycle once, then you go to a state in which not H. Here it is not H, okay? So that becomes true. And after that, you can keep going, back and forth to here, okay? No, so it is actually circulating here because both not H continues to be true. So it is, no. Okay, so you're going from not H to state in which C becomes true, and then it goes back to so you have to go here. So you go here, not H. Let me see. So not H, you go to you not H. No, I'm sorry. Not H to not C. You went to not H to C. After that, you can, there should also be, there is a transition missing here in this thing. Okay, you see, there has to be a transition back to here. Okay, just like I have it in here. So that is missing here. That's a mistake. So there has to be a transition back to T1 as well. So that is the one that mimics. Okay, that particular satisfying path in this Kripke structure, starting from 1. So you can go, it becomes satisfied. Then you can go back here, go back there, like back and forth. Okay, so that is what is the intuition. So I hope so you understand. So the reason is that the way the tableau is constructed is kind of exhaustive. Okay, it covers all possible ways as per the semantics or the thing that it satisfies. Now, in a particular Kripke structure, it may choose to mimic certain ways in which it does, and that's why it says that if there is a path satisfying here, then there will be a corresponding state here in which that formula is included, and a fair path from that state will mimic the label version of exactly this path. Okay, and that is intuitively, I hope you can see because of the way it is constructed. Okay, a formal proof is a bit lengthy, but it is mostly done by inductively using the structure of the the formula. Okay, so that is one important correctness theorem associated with the construction of tableau. Okay. So any questions here? This is only part of the story. I still have not completed, the remaining story is how exactly will you use this tableau once constructed to check if, say, this particular property for which you have constructed the tableau is true of this thing. I've just shown that, that it is, okay. One more question, that I should answer. What is the tableau for the negation of 5? See, once you construct the tableau, the states are the same. This is, I call it as a tableau for this property, not H until C, because I mark those states. The initial states of these things are the ones that contain the original formula for which you constructed the tableau. But as you can see, the tableau is kind of maximal. It includes all the maximal, all the elementary states, and it includes all the transition. Therefore, it is quite simple. I don't know if you can see it or not. This, I have a dotted arrow here in T4 and T5. So the tableau for the negation of this thing is very simple. It's just the same tableau in which the initial state, instead of being T1, T2, and T3, which contain 5, it'll be, instead of that, then you will have T4 and T5, which contain not of 5. That's all that you that you need to do. Okay. Because the transitions and the states already are maximal, and you are taking account of the negation. So all you have to do is to change the initial states, and you get the tableau for the negation of the formula. Any questions? This is important because, as you can see, so how do you model check it? What are the steps for model checking it? First, you construct the tableau. If you want to verify phi, check phi if a property phi holds good for a given crypt key, given transition system. You construct the tableau for the negation of the formula, which effectively means this, you construct with the same way as we described, except that now you have to make T4 and T5 if indeed you want to check not H until C, which is true in every state here, not only the initial state 1. So you will have to make the tableau for not of this, which means it is the same tableau with T4 and T5 being the initial states, because they contain not phi. That's the first step. Then after that, once you construct T of not phi, you take the product of T of not phi and M. Okay, I'll define the notion of formally define what taking product means. But intuitively, you kind of understand it is very much like taking products of automata. Okay, those transition systems in some ways can be considered as infinite automata. So effectively, they contain the set of all paths that are common to T of not phi and M. And since T of not phi contains, I'm considering fair paths only, since T of not phi includes all paths that that satisfy not phi, all different ways in which not phi can be set. So effectively, this product will end up containing all paths in M that also satisfy not of phi. Okay. Then you have to, okay, so because you have to, of course, filter out all the non-fair you filter out all the non-fair parts. So now you then compute all the states in this product machine, okay, that are fair. That is, you only consider those parts originating from any state here that are infinite parts that are fair. And you take the first component, the second component. Here the product is the first component, the product is T of naught phi, and the second component is the first component is the tableau, the second component is M, the machine, okay, for which you want to check the property. Yeah, so you just take all states here from which containing phi, okay. Not phi in this case, all fair parts, and you take the second component. And that you want to ensure that is empty. If this is non-empty, then you have to see if there is any intersection from that V with the initial states in this machine. If it is not empty, then there is a violation. If it's empty, then it is then it is fine. Okay, so that's how you do. Okay, so it will, the product machine, since it contains things that are common to both. So if there are parts in here from any state, fair parts in the machine M that are common with this tableau, and since the tableau is for naught phi, then that will be a path, and the state from which it starts is one that is a witness to naught of phi. As an aside, you see, this kind of enumerating all the states from which there are fair parts in this product machine is it is exactly computing this EG of true, doing EG of true with the fairness constraint as defined. And we will see that we will define the fairness constraint in the product machine exactly as the parts that are fair in this tableau. Okay, so, and doing this, computing this V is reduced to one of doing EG of true under fairness constraints, because it just true is always true. So you're just getting all those states from which there is a fair path, all those states. And if there is one, then that will be certainly preserving naught phi, which would be violating the phi. Okay, and that's how you do. So pretty much the problem is, once you construct the tableau and then the product, you reduce the LTL problem to one of CTL model checking with the fairness constraints depending on the thing. Okay, is the overall idea understood?
What are the fair states in the product repair structure?
Let me get to the exact formal definition of this thing. So this is the product machine. T is the tableau. That then the AP of that is whatever atomic formulas, atomic predicates in the formula for which you constructed the T. Okay, the AP on the right side of M will include, of course, these AP of F, but it may include other things, other predicate symbols also. Okay, that's why we have kept I've kept these two things separate. It has its own relation. This has the relation as constructed for the tableau. So the states of the product machine are just the this is the cross product of the states of this, but there is a constraint that this when you you will have to the atomic predicates in the state will have to correspond. Okay, so when you restrict the state of the Kripke model, that in that when you restrict that to APFF, that it should be the same. Okay, the two states must have the same atomic predicate as far as from the point of view of the formula. Okay, only then only if there are only then the product makes sense. So S0 is an initial state in the product machine if both the states are initial. Yeah, this is pretty similar to the way that you would take the intersection of two automata. And this label in the automata, both the transitions will have to, the labels are on the transitions, whereas here they are in the states, okay? And that's why, the first constraint is on the labels contained in the state. Yeah, so the label for the product machine is as per the tableau. And here is the question that Kapil, you asked, and Diganta, you also asked last time. So it's exactly the same, identical to FT. So if it is, since there is no fairness on SM, so it is just the fairness constraints or just the constraints as derived from whereas these PIs are the fairness constraints of PI are just inherited from the tableau. That's all. So it's only you only have to restrict yourself to those parts in the tableau. I mean, restrict yourself to those parts in the product machine that are that are fair in the tableau. That's why you use the same condition as on the first component of the state. Okay, so that is the formal definition. Here is an illustration. So after this illustration, I'll stop. So as I said, there is a mistake here. So there are some transitions missing that you will have to correct. So if you want to check not H until C, what you have to do is to take the negation of this. And as I said, the negation for the tableau is exactly the same thing, except the initial states are T4 and T5. And AP of F, this should be F, is not H and C, but you will have both its positive and negated in a fashion. So these are four possible combinations of the atomic predicates. As I said, you will have to only include those states in the product such that they are the same. So if you can see, H0C state doesn't even exist in M, although they are there here because the tableau is exhaustive, okay? Whereas here, those states are not even there. I mean, included. I mean, he could include those things, except that they won't have, they won't play a role. That's why. So that those states are not there in the product machine. Otherwise, then I'm matching up for not H, not C. Okay, there is T1, not H, not C, and here there is 1, 2, 1 and 2, not H and not C. Those are the only two states. So you will have these 4 states that have not H and not C, both in M as well as not C, as the possible cross product in states. And HC, yeah, similarly. So you do that. Okay. That's clear, right? Okay. So then you do then you make the transitions. Yeah, I've included both this and this. You should consider, since T5 is the T4 and T5 are the thing, and T4 will not figure. So your product, the initial state of the product machine that is of concern to you is the one in which there is this dashed edge, that is T5-1. T4 doesn't even appear here because as T4 has H not C, and there are no states in the product machine corresponding to that because there's no H not C there, and therefore that gets completely eliminated. And if you follow, I've constructed this exactly following this thing that there must be a transition. Once you match up the states, there is a transition in the product machine if there's a transition in both from that state in the product machine in the Tableau as well as M. And that's how I've constructed here. And then after that, what do? You will have to collect all states here from which there are that contain this negation of this. I mean, which is what here this is. From which there are fair. And you see that T5, in this case, T5-1, from T5-1, there's no from not 5, the state that contains not 5 is the only state is T5, okay, because T1, T2, T3 are all contain 5, okay, T4 got eliminated. Therefore, you see there is no outgoing edge at all from the product in the product machine in the product state that has T5, okay, because that's the one, the only one that contains not 5. And therefore, the set of states that contain not 5, from which there is at least one fair path going out of it, is empty, okay? So V in this case is empty in the product machine. This is the only state that contains not phi is T phi in the product machine, and there is no outgoing edge at all, okay? So V is empty. So that's why what that means is that there is no error path in the thing. So every state. So that's why. So what you start doing, your goal was to check not H until C. Okay, and the P was constructed using T of not phi, and then taking the product machine. And in that, you will check for EGF true if there are all the states that contain F. Okay, I mean phi. So this is true. So and that is empty here, which means every state in SM is such that every path from that phi holds good, which is what So so of course you're interested in the initial state, but this method, computes all the states from which that
It's empty because there is no unfair path here, right?
there's no path at all. There's no fair path. Okay, there's no path at all. Okay, going there. So you're only looking for fair paths. Okay, so in this you have to look for fair paths.
Start from T1, 1, right?
Huh?
Wait, I'm confused. Where do you start from? T1, 1, right?
No, you should start from T5. T5. You see the product machine. You should consider what you need to check is V is that if there are fair paths from states that containing phi, okay, in the product machine. So I mean, when I say containing phi, in the first component in the T5, in the first component of the product state that has phi, okay, which is T5 here, and which is containing not phi, okay, because we're checking for phi and it is not phi.
Okay.
So T5 is the only one that has not phi.
Okay, yes.
So V is the set of all states from which there are fair paths, set of all states that contain not phi, okay? Set of all states in the product machine whose first component contains not phi, if I have to be very, very specific, okay? Because the second component are the states from M, they don't contain formulas anyway, correct? So when I say, the state in the product machine that contains a formula, it means the first component, okay? Not phi. So in this case, it's T5, okay? So you could, if there are other states, now if I were doing, for example, H, if I were doing checking not of phi, suppose not of phi, yeah, so yeah, so okay, if you want to check not H until C, you took not phi, and there you expected V to be MT. Okay. Now, if you want to check if there is violation for the negation of it, then you would consider. So you look at T1. You ask T1, Kapil. Okay. T1 is the initial state that contains phi, okay? And you see, there are fair paths there. If you look at this, there are fair, paths as defined for phi, okay? So you go from here, you go like this, you follow this, and then bing, 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 bing. So you do this. There are paths there, okay?
So a fair path means that it passes through some fair state.
No, that's the fairness condition corresponding to phi, okay?
No, I'm just asking fair path means that so there are some fair
Both
states.
paths on which the fairness states for F5, okay, happen infinitely often.
Not all states, some of them will do.
Yeah, some of them will do, but in this case, the infinitely often is, either happens here, T3, you see T3, T2, they both are included in what I've marked as double, in double thing here. T1 is not included in the, is not a fair state, okay? So as long as you have T3 is 1, so there is a fair path from here, goes all the way here, and then it circulates here, okay? T3 is fair state. That happens infinitely often, and all these T2, T2, T3, T1 is not. So all these are fair. Okay, so there is also, you see, there is loop from here also. Okay, there are several fair paths starting from a T1. And since T1 is a phi state, so what that means is that, and you will see that those states, so they, so phi 1 is true in all those states. Okay, so from every state, in these paths, you see T1, T2, T3, T5, T7, all of them are included in here. There's no T7, I'm sorry. T1, T2, T3, T4, T5, So if you look at this, I'm sorry, if you look at this, so 1, 2, 3, 4, 5, 6, 7, all the states of M are included in this, okay? So what V is those states, okay, in which that will include everything, okay. So so that's why they are true. Not H until C is true in every state, okay, of that. Or if, since V will include everything, 1, 2, 3, 4, 5, 6, 7, I mean, when you subtract this, that not H until C, the states in which not H until C are violated is empty. Okay, that's what it means. So if you were to compute the negation, check the negation of this, you would take the negation, then it becomes not H until C. Then you would be doing the fairness check from a T1, okay, and then fair paths check from with the initial state as T1 or T4, T1, and then that you will see will end up where in which V will include all the states of M. Okay, and when you subtract it, it will say, okay, the states that violate that is is empty. So that's how you compute. Yeah. Yeah. So in order for you to do it, so if you want to check those states in which not H until C is true, you will end up getting empty. Okay, because SM minus V will include everything, and SM minus V will be empty. So the states in which that satisfy negation of this formula is empty, because every state here satisfies not H until C. And that's what is indicated by, you see, the fair paths of, there's a fair path from every state whose second component is all the states in the M machine here, as you can see in this part. So finally, so here is what my main correctness theorem. So let T phi be a tableau for an LTL formula phi, and for every Kripke structure M and every path pi prime of M, if M of pi prime of M is true, this pi prime satisfies the path, then there is a fair path pi in T phi starting in a state S such that phi belongs to S, and label of pi prime will be equal to label of pi. Okay, so that's how the correctness theorem is stated, and the way you will use for model checking is this way, by collecting all the states from which there are fair paths. Okay, and so that gives you all the states, and then you can check it with respect to the initial states, or you can keep all the states however you want. So that's how it is. Yeah. Okay, so so if you have any questions, I know it's late, so you could review these slides and have any questions. Next the last class, which is on Thursday, I will spend just for revising any questions that you're going to have on all any of the topics that we have discussed until now. I know that I had promised that I will make up some sample problems that I'm still working on at the time, and I will certainly do it. Okay, if not, try to do it before Thursday. If not, certainly I will upload it. Okay, so that you will have some thing to work on. Okay. Yes. Any questions you have?
So how does this compare to, say, BMC for, like, I know BMC is not complete, but this is complete, right? So, but still in terms of performance, how does it compare?
Yes, but if you can find the thing, it is find the completeness threshold. You see, the number of states of T of the tableau is exponential, okay, because it sets up all subsets. It's exponential in the size of the formula, okay, and you cross that, okay, the size of T phi in the worst case is exponential in the size of the formula. Correct?
Right.
And you're crossing that with S.
Yeah.
I mean, the size of M.
But we will be doing that symbolically, right? So, I mean, in the CTL, like,
that is true. That's true. I'm saying I'm just talking about the worst case complexity. Okay, the worst complexity. That's what it is. So now, if you're representing these things symbolically, then it is still the recurrence diameter. Okay. No. So you could do this. Yes. And then it is CTL model checking. See, CTL model checking, I mean, I think I'll review the thing. CTL model checking, each iteration, fixed point iteration is, in the worst case, it can be the number of states, no?
Yeah. So it's bound to be much less efficient in that sense.
Number of steps there. Okay, so that is exponential the size of the formula and the thing. So, and then you will have to check with fairness, okay? The fairness constraint. So it'll be the fairness constraint, and even although you're doing symbolically, yes, you're doing symbolically, and then, but it'll be the longest distance to any of the strongly connected component, okay? Because fairness checking is really, even in symbolic, you're covering all paths simultaneously to several SCCs, okay? Because they are kind of lassos, okay? They end up doing lassos. So you will have to do that. Yeah, so the number of iterations, what I'm saying is before you reach the fixed point, I mean, at each level I'm saying, okay? So maybe I'm mixing, I don't know. I mean, if you do it symbolically, what is it that you will gain, what you will get, I don't know. I'm looking this as a worst case complexity of the thing. So in each step, the number of states, which is what is bounded by the number of iterations you take for reaching a fixed point, okay? And the number of iterations you will do is the, here the number of iterations is just the fair paths. It is not, because it's EG of true, okay? What you're checking is EG of true. And So it is kind of completely reduces to the, I guess it's not even, see, it's EG of true. Therefore, you should get in one iteration because you're not doing nesting of fixed points in the, if it were a nested formula, it is true.
Right.
Yeah, they're bad. So that's why it will reduce to, and that fixed point convergence at that level, it will depend on the longest, the recurrence diameter, okay, of recurrence diameter of this product machine, okay.
Right.
That something like that, and that of course the recurrence diameter can be as long as your state space itself, okay. It may not be, okay. That's why you remember that I was saying I used this result, this Tableau method, as good, you know, when I observed, okay, why should there exist a completeness threshold at all for bounded model checking? I said, hey, look, this is as worse as it can get, okay? The recurrence diameter of this product machine, okay? You can certainly use this recurrence diameter of the product machine if you can compute as the really worst case thing, yeah? So that's how long it can be, okay? So there's only one fixed point iteration here, but in the presence of fairness constraint. And when you do fairness constraint, you really have to check because you're also including that fairness restriction. You have already implemented the presence of fairness constraint as part of a fixed point check inside a fixed point check, correct?
Yeah, yeah.
And that fixed point inside the fixed point, that inner loop can take that long, okay?
Right. So I mean, in worst case, this might even be like much worse than a direct BMC up to threshold.
Yeah, but if you can compute the threshold, you know, for any particular transition thing,
then that is probably much better.
yeah, but here also for that particular thing, you may converge faster, so you don't know.
Yeah,
huh?
yeah. So is this used in widely in practice, or is BMC more preferred? Is there anything like that, or is it?
See, what else will you do? I mean, because that method is not complete. If for simple properties, you can use that. Otherwise, you know, what do you do? So I think these are implemented, but look, so maybe it's getting late. So we'll continue this discussion, okay? So, you know, I will kind of summarize what the complexity things are. So yes, okay. This question that you that you asked is requires a long, winded answer. Yeah. So not as simple as that. I mean, if you see if it is implemented, yes, it is implemented because before SAT solvers came, this was what was implemented. Okay, all these was implemented using BDDs.
Right. Yeah.
And in the new SNV, first initial versions had only BDDs. Okay. And this is the method that they were using. The bounded model checking came much later, like after 2001 and 2000, in the decade from 2001 to 2010. Yeah. So yeah, but if it's not complete, I mean, the answer to your question is I don't know. I mean, in practice, it's hopeless if you do very complex kind of a thing. So most properties will be very shallow, okay?
Right.
And so if you can get the completeness threshold, I'd rather use that thing. And if it's for safety, all safety properties have a recurrence diameter, okay?
Right. Yeah.
I would just use the recurrence diameter of the transition system. Only for liveness that you will have to do this, but there are other methods to, like I said, this is one way of reducing liveness, okay, to checking kind of safety, yeah, because the CTL plus fairness, huh? So this is one way, but there are better ways to check liveness properties, yeah. And I've given one reference in that thing by Armin Beer. Yeah. So, but your question, I don't have a definitive answer. I mean, I have kind of a general answer like that. In practice, I guess for most practical things, especially for safety verification, people use only bounded knowledge, even with completeness threshold. And if it is simple liveness properties and so on, I just use bounded knowledge.
Right. So this is like a much more special case application sort of a thing. Yeah. Okay.
Using K induction is better, right? Instead of using this.
That's true. The inductive methods are definitely the, of course, the inductive methods all work for only safety properties, by the way.
Yeah, yeah.
And for safety properties, I would do inductive methods if they work, okay? I mean, I didn't get the time to discuss one method called IC3, which is the best inductive methods. But I think you're right. This comment is good. I think the ones for safety properties, mostly, if you want a complete method, it is the inductive methods. Okay?
So IC3 is that abstract interpretation or something, right?
No.
Okay.
Not. If any of you is interested as a project, I'm more than happy for you to engage in something related to IC3. Okay? IC3 at the Boolean level is a done deal, okay? But it is there in almost all things, and it's even used in industrial practice. How to extend IC3 to more sophisticated data types, that's still very much an open problem, okay? IC3 is the best inductive method that kind of exists to this day. And that works well only for Boolean logic, propositional logic, not for arbitrary logic. If you're interested in looking at IC3, etc., that would make a good master's project. Yeah, if you're interested. Okay, I have to stop, okay, to be fair for yeah. So I'll see you next class. We'll have fun next class, okay? Just open-ended discussion, yeah? Or any specific questions. Thank you.